Hi there, it's Chem Coach Powers, and we're ready to go again with another lecture on some amazing stuff with solubility. We're talking about solubility and concentration today, and this is section 8.3 from your text. Today, our objectives are going to be to distinguish between saturated, undersaturated, and supersaturated solutions. And then we are going to calculate concentration and figure out what it means to have solubility calculated as well. And then we're going to interpret some solubility curves. This should be exciting, right? All right, so what is soluble? Soluble basically just means something that's dissolvable. Okay, so if I can dissolve a substance in another substance, then that substance is considered soluble. If it's not soluble, then it's not dissolvable. So for instance, oil does not mix with water. Oil does not dissolve in water. Oil is not soluble in water. Oil is insoluble. Okay, went through all that. Salt would be soluble in water. Now, there are things that would be soluble in oil. For instance, the gasoline might be soluble in oil. Various different things that are nonpolar can be soluble in things that are nonpolar. Okay, so the solubility of a substance is defined in a couple different ways depending upon where you are, but this is a standard definition. The maximum mass of solute that can dissolve in 100 grams of solvent at certain temperature and certain standard atmospheric pressures. Okay, so if at standard atmospheric pressure at a particular temperature, how much can I dissolve of this substance in 100 grams of water or in 100 grams of a solvent? That's how we would typically define solubility. So you can calculate solubility by taking 100 grams of that solvent and then having your total number of grams that you were able to dissolve into that divided by the 100 grams of solvent, and you've got a value for solubility. Okay, so solubility is also defined as the ability of one substance to dissolve in another at a given temperature and pressure. So you'll notice that we have two different things here. One in yellow says that it's specifically can be calculated based upon 100 grams of solvent. And then the other one, which is the definition that you have in white there, is just talking about its ability, okay? Solubility, its ability to be dissolved in another substance, okay? So one is a calculated value, the other is a general definition. Both of them are used, and you just want to make sure that you realize that they're both used so you know which one to talk about. So for instance, I can talk about the solubility of these various different substances. I can see calcium chloride has 75 grams that can dissolve in 100 grams of water at 20 degrees Celsius. And that's a pretty decent amount, it seems like. If you look all the way down to the middle of the chart, you see silver chloride, and silver chloride is only dissolving 0.00019 grams in 100 grams of water. So you can see that some things are more soluble than other things. Some things can dissolve in greater quantities in 100 grams of water or a solvent than other things. Okay, so not every substance has the same solubility. And the solubility has to do with the intermolecular attractions that are involved between the water and that substance, as well as the attractions that that substance has for itself. So for instance, we could probably bet that silver chloride is way more attracted to itself than it is to water. And that's why it doesn't want to come out and get surrounded by water, and water can't pull it out and make it dissolve. Okay. All right. So how much of a substance is in a solution is basically considered your solubility, right? And we have ways to express this. One of them is called the concentration. Concentration is the amount of a particular substance in a given volume of a mixture, solution, or ore. Now, few different ways to calculate concentration. One of them is through molarity. The other is, well, there's lots of different ways, but we're going to talk about molarity briefly, and we're going to talk about another value which has to do with percentages as well. Now, we have two terms that we can describe concentration with. One is concentrated, the other is dilute. If something is concentrated, that means that there's a lot of that solute in the solvent. And if something is dilute, that means there's a little bit of that solute in that solvent. Now, these are relative terms, and they're a little bit arbitrary depending upon the substance, right? But that's the idea here. Concentrated means you have a large amount. Dilute means you have a small amount. And if you want to dilute something, that's actually used as a verb in that case, then you would actually be adding more of the solvent in to decrease the concentration. So to dilute something is to decrease concentration of a substance, okay? All right. So here you have an example here with these pictures. You can see over on the left, you've got something that's dilute. It's only got a few of these little particles in it compared to over on the right where you have a lot of these little pink particles, right? An example of this would be coffee. Now, not that coffee is necessarily dilute, but compared to espresso, which has a much greater concentration of caffeine in it, then you could say, oh, the espresso is more concentrated, the coffee is more dilute. Make sense? All right. So let's look at some of the ways that we calculate these concentrations. Now, like I said, one of the terms is called molarity. You can see that there in yellow. And this is one of the most common ways. We use this in chemistry pretty exclusively. When you take chemistry, you're going to see this used a lot. We are not going to use it here in physical science, but I do want to make sure that you understand the concept. The concept is a certain amount of moles of a solute per liter of solution. Okay, so if we use molarity, we're saying you have this many moles of a solute per liters of solution. We don't use that much here because we don't really get you super familiar with the term molarity and the term moles, right? And how to do moles. But that's the calculation basically. It's moles per liter, right? It's pretty easy, moles per liter. We just don't have to worry about it here. Now, this is the one that I do want you to know, and this is a simple percentage expression that we use typically, okay? So we'll talk about the percentage concentration of something, or we might just use brackets. And if we use those brackets, we won't use a percentage value, okay? The brackets basically are saying this is the concentration, which you could kind of pretend to throw percentages on there if you want to, right? So for instance, like I said, if I had a 1.0 molar solution of sodium chloride, it would contain 1.0 moles of the dissolved sodium chloride in a 1.0 liter total volume of solution. Like I said, we won't really use that. We're going to use this concentration one, which is super simple. You take the grams of the solute and you divide it by the grams of the solvent and then multiply it by 100. And again, you put it in brackets to say, hey, this is concentration. So let's practice that. Here I have 12.8 grams of sodium chloride in 20.0 grams of water. So what would that look like? Let me get my pen here. And we're going to change our color. Make sure it's nice and easy to see. Oh, you didn't see that answer, did you? All right, so we're going to take our grams, 12.8, of the solute, and we're going to take our 20.0 grams of our solvent. We're going to multiply that by 100, and we're going to get our value. Okay, so if you pull up the calculator, come on, calculator, pull yourself up. There we go. All right, and then we just take 12.8 divided by 20. You get 0.64. But if we multiply that by 100, then we're going to get 64, right? And so our value, we would express in brackets, is going to be 64, okay? Now, these grams are basically canceling out, even though they're not the same unit up here. And so we get 64 as our concentration. We might also see somebody express that as a 64%, okay? That is the concentration. Now, I want you to try it on your own with the next one, all right? Number 2, it contains 0.10 grams of sodium chloride in 15 grams of water. What are you going to get? All right, pause and practice. And you're back. And you hopefully took the 0.10 grams of sodium chloride, divided it by 15 grams of water, and you got, even after you multiplied it by 100, you got 0.67. Okay, and so if I were expressing that, and again, you'll notice that expressing the units here is a really great way to do it. Oh, wrong thing here. Expressing the units here is a really great thing to have that whole set of units so you know what it is. But you know, the value, if you just express it in the concentration in the brackets, that's another fine way to do it. Okay, so you can show the whole unit, or you can just show the little bracket part. Would prefer you didn't do 64% right now, but that's not necessarily a wrong way to do it either. We would just want to say 64% by mass is how we would usually append that. We'd add that little by mass to the ending there. Okay, so I'm going to have you do another one. And you'll notice we did attach some adjectives here, dilute and concentrated. Like with respect to each other, since this is both with salt, this one up here is way more concentrated. This one's a lot more dilute, okay? Much more salt versus much less salt. All right, now I want you to pause and practice this one as well, but pay close attention. If you're not paying attention, you might mess something up here, right? So, all right, ready, pause it. And you're back. Okay, so what was tricky about this one? Well, what you might have or might not have seen is that we swapped places, okay? Instead of the water being on the right, we put the water on the left. And we said it contains 13 grams of water containing 0.50 grams of barium chloride. And so we just got a little tricky on you. But you were probably smart enough to catch that. And so that's the way you should have done the math there. So what would that have gotten you? That would have gotten you 3.8 grams of barium chloride for every 100 grams of water. You know, again, that was after you multiplied it by 100. So, sorry, I got to do that 100. So you could have put a 3.8 in brackets, and that would have been a fine answer as well. All right, so let's talk about our different types of solutions. What do we mean when we have a saturated solution? Well, if we can't add any more solute to our solvent at that given temperature, I have saturated it. I've made it so that no more can fit in. I've dissolved every last little bit. That's what a saturated solution is. If I were to drop one extra little crystal into a saturated solution, it's not going to dissolve. The little crystal will fall to the bottom. I'll stir and stir and stir, and that little crystal is still going to be like, okay, I'm not dissolving. All right, that's a saturated solution. You add more solute, it just settles to the bottom of the container. So saturated solution is a solution that cannot dissolve any more solute under the given conditions. Unsaturated solutions can become saturated, right? So an unsaturated solution is something that can have a little bit more dissolved into it still, right? I can still add a little bit more and it disappears. So if I have an unsaturated solution, put a little in, dissolve it, it's gone. Okay, it's not gone. It's actually just mixed in, right? But it's mixed in a homogeneous way, so it's a homogeneous solution. That is a great way to know that if you have an unsaturated solution, you drop a little extra crystal in, and it will dissolve. Okay, you can also do something to make a saturated solution dissolve more material, and that is to heat the saturated solution. Now, what happens is as you heat a solution, you know, with anything, heating causes expansion. And so that liquid is expanding. And as it expands, it's actually allowing for spaces for more solute to, you know, have the opportunity to get in there into a solution. And so it actually expands, allows for more solute to dissolve in. There's also lots of, you know, more speed with the particles of the solvent moving around and colliding and maybe making more attractive more opportunities for attraction because things are expanded out a little bit more. But really the biggest thing here is all about that expansion, giving more space for particles to fit in between all those little spaces. So solubility of solutes increases with temperature. And we do put the word most there. And the reason that we're putting the word most there is because there's definitely some exceptions, okay? But most are going to increase in solubility as you increase in temperature. So what's a saturated solution then? It's a supersaturated solution. It's one in which you can basically put more in the liquid and that solvent than you really should be able to hold at that given temperature. The only way to accomplish a supersaturated solution is to heat the substance up, excuse me, and then to allow that substance, after you've dissolved more stuff in it while it's hotter, to allow that substance to cool. If you can do that, you create basically an unstable situation where these particles are being held in place, but they're not exactly happy. And it's not going to take much to get them to come out of solution. and suddenly you have a crystal that will form. And so what happens is if you add just a little bit more solute into a supersaturated solution, crystallization begins to occur. And what's happening there, again, you have to realize that in a supersaturated solution, you've got those little ions that are actually being held and surrounded by the water. But once you add a little seed crystal, and that suddenly allows for a shape or a pattern of crystallization to be modeled after, those ions start to attach because there's not enough water to keep them in that unstable state. And so they start to attach to all of the other attractive forces that are right there. And all of a sudden, instead of the water being around the outside, the water is now oftentimes actually absorbed into the crystal itself. The crystal can actually hold the water inside of itself. And that's what you'll see with the sodium acetate. And when that reaction, well, it's not a reaction, but when that transformation takes place, it's just really cool because the water goes from being on the outside to being on the inside of the crystal. And it seems like the water just disappears. It's like liquid turns directly into solid, and it's not freezing. Okay, it's actually giving off energy, which freezing actually does too. But the whole process is that as it goes from outside to inside, it's going to a more stable energy state. And that more stable energy state is one in which it's going to allow for energy to be released. So it's an exothermic process. So let's have a table here and go ahead and make this table so that you can see what it is that we have as we kind of summarize all of these things. Okay, so take a second, pause, and write all this stuff down. But basically, saturated solution, maximum amount of dissolved solute at a given temperature. Unsaturated has less than the maximum. Supersaturated has more than the amount that should be able to be held in there at that given temperature. Examples: saturated solution, you might have 36 grams of salt at 20 degrees Celsius in 100 grams of water. Unsaturated would mean you'd have less than 36 grams. So maybe you have 35 or 32 or 9, whatever. And supersaturated would mean you'd have to have more. So like 36.1 or 35, 55. 20 plus 30 is 50. 20, 30, 50. I just can't even speak numbers anymore. Yeah, it's Thursday, which is typically my second Friday of the week. All right. Additional crystals. What happens if we add an additional crystal to a saturated solution? It doesn't dissolve. And unsaturated solution, if you add an additional crystal, it will still dissolve. And a supersaturated solution, if you add an additional crystal, it's actually going to cause the formation of a lot of different crystals. All right. All right. Saturated solutions can either be dilute or concentrated. Remember that the saturation does not have to do with whether it's concentrated or dilute. Some solutions are saturated at very, very, very little, like we talked about with the beginning with silver chloride, 0.00019 grams per 100 milliliters of water, right? So you're talking about very, very little that will dissolve in it. It's saturated and yet it's dilute. Okay, so you can have saturated dilute, you can have saturated concentrated. Saturated and those dilute concentrated terms are not the same. Saturated does not mean concentrated. Okay. Unsaturated solutions can be dilute or concentrated as well. And supersaturated solutions are, again, you have to remember that you need it to be heated up while more stuff is being added, and then it cools down. That's the only way you can get to a supersaturated solution, is by allowing it to cool down after it's been heated and had more stuff added to it. All right, now we've seen, and we're going to see another graph here in a little bit, how solids become more soluble in water as the temperature increases. But gases do exactly the opposite. Gases are going to become more soluble in water as the temperature decreases. Now, you have to remember that as these particles are bouncing around, the water particles are moving around. As the temperature gets higher, the particles start moving around faster. And honestly, that's just knocking the gas right out of solution. All right, so the faster it goes, the less gas is able to hold in. If those molecules are slowing down, then the gas is able to be kind of held on to a little bit better, and it's definitely not being knocked out like it was before. All right, so gases are going to become more soluble in water when the pressure increases and when the temperature decreases. Why does pressure have to do with it? Remember, pressure doesn't really have anything to do with the solubility of solids. But with a gas, if I push on the substance from above, in order for the gas to escape, it's got to overcome that vapor pressure is what we call it. And so if I increase my pressure above, my atmospheric pressure above, or my chamber pressure, however you want to talk about it, then it's going to have even more atmosphere or even more vapor pressure to be able to escape. And so it just doesn't escape as easily. So think about a soda can. You open it up and all that fizz that comes out, that is the escaping gas. It was under high pressure, and so it held the gas in solution. But as soon as you open it, all the bubbles start forming, right? You see all those bubbles inside there as soon as you open it up? That's because it's no longer under pressure, and so it can't hold as much gas in solution like it did before, and so they come out of solution. And as soon as they start bubbling, it's not a homogeneous solution anymore, right? It's a heterogeneous solution because you can see the bubbles inside. All right, so that's what we're talking about here in this picture. Again, if you have a picture in your mind of what this gas would look like right at the surface between the liquid and the air, you've got all these carbon dioxide molecules inside the liquid and outside, and there's an equilibrium where they're passing and they have an equal amount going in and out, right? Well, as soon as you open it up, now these bubbles, these carbon dioxide gas bubbles, right? These are bubbles of a bunch of carbon dioxide all connected together in a sense, right? They're able to now escape and go out because there's no pressure pushing them in and holding them in. Here we got these little particles here. This is probably, here's your carbon dioxide, and this is probably like nitrogen, and that's probably oxygen or something like that, right? So that's the atmosphere that's involved there. Okay. All right, now, couple cool videos here. And again, I would encourage you, if you're watching this video at home, click on that video and find that link, and you're going to see sodium acetate crystallization. You can also look up hot ice. This one is kind of more of the same type of video, but it's a little bit longer, goes into a little bit more detail, shows you how you can create a column. As you pour liquid out, it turns into a solid right as it contacts. It's really cool. So these are really neat little demonstrations of a supersaturated solution basically going from a liquid to a solid very, very, very quickly. Super fast crystallization. And the reason it's happening, again, is because the water that's all surrounding it suddenly gets incorporated into the crystal structure. It's an amazing thing to watch. So watch those if you have an opportunity. There's lots of them on YouTube. You can watch different forms of hot ice or sodium acetate forming. Okay, so to finish up here, let's just talk about this graph. Now, this graph is one that it's called a solubility graph, and it has a bunch of different solids dissolved into 100 grams of water. And the different lines that we see here with the different colors are different substances. And you'll notice that they all have slightly different characteristics with regard to how much can dissolve in a particular amount of water. But they, for the most part, are all trending upwards, right? That as you increase the temperature down here, I'm going to change color of pen again. As you increase the temperature down here, that almost all of these are increasing, right? So all the different solubilities, most of them are increasing. There's one that's not. If you look at this line right here, this is the cerium 3-sulfate. You can see that one is not increasing. It's actually decreasing. There's always exceptions to every general rule, right? But, this graph should be interpreted like this. I have, let's say for my sodium nitrate here, if I look right where it intersects the line at 0 degrees Celsius, then I can see that it's probably right at about 72 grams of sodium nitrate dissolved into 100 grams of water. Okay, so that's your solubility. That's the calculated solubility, right? 72 divided by 100 times 100. Okay, it's 72. Okay, so my concentration of sodium nitrate at 0, I would talk about a concentration of 72. Now, you'll notice that sodium chloride, way different, right? That's about 34. If we look at potassium chlorate, you're down to like 4, right? So all these different substances have different solubilities. This graph is what you would use to read those different solubilities. And you can also say, well, what happens at 50 degrees? at 50 degrees, how much potassium chloride can I have, basically? Well, you'd go up to where potassium chloride line intercepts, right? That 50 mark, and you come over and you're like, oh, well, it's about, 42, 43 grams of the so potassium chloride is able to be dissolved into my water, my 100 grams of water at 50 degrees Celsius. Now, if you pay attention to each of these lines has to do with saturation, unsaturation, and supersaturation. If I think about, let's go back up to this sodium nitrate. If I had 65 grams dissolved, then I could still dissolve another 7 grams before I got to 72. So anything under the line is considered an unsaturated solution. Anything that's on the line, this line is the line of saturation, okay? Anything that's on the line is considered saturated. That's the most that you can dissolve at that particular temperature and pressure. And then anything above the line is going to be supersaturated because I've got more in there than I should be able to hold at that particular temperature. So if I had 75, that's more than 72, which is all I should be able to hold. So I must have heated it up, put more in, and then cooled it down so that it was there at a slightly unstable form. Okay, so now you kind of know what these solubility graphs are all about. And you've studied and learned about all this good stuff here. Let's see if you can do what we set out to do. Can you distinguish between saturated, unsaturated, and supersaturated solutions? I think you probably can, right? Saturated, as much as it can hold at a given temperature and pressure. Unsaturated, I can still put a little more in. If I put a little crystal in, it's going to dissolve. If I put a little crystal into saturated, it's going to just sink to the bottom. And then supersaturated, more than it should be able to hold, and it's unstable. If I put a little crystal in, it's going to start to form a crystallization process right away. Now, not all of these supersaturated solutions are going to, completely freeze up like the sodium acetate did in the video that you watched, but they will at least form some crystallization process. And then, can I calculate concentration and solubility? Well, sure I can, right? We learned about concentration. We learned that you could calculate concentration in molarity, although we don't really do that one. We just did the grams of solute over the grams of solvent, right? And then we multiplied that times 100. So that was our concentration calculation. It was pretty easy, pretty basic. And we learned that, hey, solubility is that, all right? As long as I'm talking about 100 grams of solvent, that's my typical calculation for solubility is what's the amount of grams of solute in 100 grams of solvent. And then can I interpret solubility curves? Yeah, and in general, just remember, solids are increasing with increasing temperature, and the gases, remember, are decreasing with increasing temperature. So my gases are going to go down in the solubility. And then just remember why that is. All ties back into the kinetic molecular theory, right? Okay, you learned lots of great stuff, and I hope you had an awesome time learning about solubility. I had a wonderful time teaching you, and I hope you have an awesome day. Be kind to one another. God bless you.